All right, today we're going to go over polynomials, and we're going to review a few familiar functions. At least they should be very familiar by this point in time. The identity function, the square function, and the cubic function. So the identity function, of course, that goes through like this. Right, just a straight line, the identity function. Square function, of course, that is a parabola centered at the origin. So right one, left one, go up one, right two, up 4. So 1, 2, 3, so about up there and right there. And so our graph goes something like this and something like this. Cubic function. Okay, through the origin, right one, up one, left one, down one. Draw it through like that. And so there it is. We've got 3 functions. And so the identity, the square, and the cubic function, these are functions we want to make sure we have down really well, because that's going to help us with identifying the shapes of different areas of a polynomial function. So oftentimes you see these summed up in this way. A3, where A2 and A1, A0 are all coefficients. That is just numbers. So, and note that we've got a cubic function, a square function, a identity function, and a constant function, all added together. So this is what we call a polynomial equation. This would be a polynomial equation of degree 3, because that is the highest exponent you see there. Now, polynomial is one of those words with a Greek prefix and suffix. Poly meaning many. And nomial meaning names. So many names, right? And the name should make sense because we're adding different types of functions together. So again, note that the highest exponent in the equation we just looked at is 3. And so therefore, this polynomial is a third degree polynomial. All right, so we're going to do a third degree polynomial with coefficients of 1/100th, 1/10th, and then 10. Note that for the identity function, the coefficient is just 0, right, because it's not present. And we're going to look at how the different terms affect the output for different values of x. So when x is 0, we plug that into here, and of course, the first term here, y equals 10, that stays at 10. Here, x is 0, and there is 0. So what controls what's going on? The constant function controls the output of the function. What about when it's -1? Of course, this is still 10. As a matter of fact, let's go ahead and just fill this out because it's going to be 10 across the board, right? Doesn't matter what x is doing. Now for x squared, when x is -1, well, of course, it'll still be 1/100th. Right, so that's 0.01. And when we get -1 here, of course, that will be 1/1000th, or -1/1000th. So -0.001. So you can see the constant function still dominates, but things are beginning to change now. When we get to -2, of course, this becomes 0.02, -0.002. Still dominating, right? But, Numbers are increasing, but now we get up to x equals -10. And so this would be 100 divided by 100. So now it becomes just 1. And for the x cubed, right, that we're plugging 10 there. So this will also be 1 because 10 cubed is 1,000. 1,000 divided by 1,000 is 1. And so, or should I say -1. And now we can see that, even though these two numbers are canceling each other out, they are having a much bigger impact on the output of the overall function, right? Because remember, the overall function is the sum of each of these columns. So now we get to when x is 100, well, that's 100 squared. Let's go ahead and write this out. 100 squared divided by 100. Well, obviously, that's going to be 100. So now this term has a lot more say in what's going on, but we'll see over here, right? We've got 100 cubed divided by 1,000. Well, note that 100 cubed is just 10 squared to the third. We'll do a little exponent review real fast. And then down here, of course, we've got 1,000, so that's 10 to the third power. And so this is simply 10 to the 6th divided by 10 to the third. 6 minus 3 is 3, so we got 10 cubed, or 1,000. Don't forget this is negative over here, so this is negative 1,000. So you can see by the time you get to x equals 100, this cubic function is dominating the function more than any other of these three terms. And so what we want to take away from this is that the lead term that would be this term right there, that's the lead term, dominates for large values of x. And since the end behavior of the lead term is 3, and don't forget that's the term with the highest exponent, and this term dominates for a large value of x, then the end behavior of the polynomial is also cubic. Right? Like what you see right here. Now, what's going on in the middle, we don't know. But we know that the end term will be, or the end behavior will be down then up, just like this function here. All right, so this pattern of the end behavior following the lead term follows for all polynomials. So we're going to be doing this for every polynomial. Identify the lead term, the end behavior of that lead term, and that's the end behavior of the overall polynomial. So in general, the polynomial looks like this right here, right? This is of degree n, where n is any natural number. And remember, a natural number is a whole number that is more than 0, right? You don't include 0. It's just got to be more than 0. So 1, 2, 3, 4, 5, 6. These are natural numbers. All right, so for this next 3 exercises, I highly encourage you to pause the video and try these 3 exercises on your own. Identify the lead term, the degree, the lead coefficient, and end behavior of the following polynomial equations. So the lead term, we're going to call it LT for lead term. Highest exponent, 2x to the 6th. That is the lead term. Lead coefficient, we'll call that a sub 6 to match the 6th exponent, is 2. Right? That is it. And then the end behavior, well, x to the 6th, that's up, up. Right? We know that because of the lead term. All right, good. Now let's look at the next example. We've got this guy here. This is the highest exponent, so that is our lead term. The lead term is negative x to the 8th. The lead coefficient is negative 1. And so while 8 being an even exponent here, well, that would usually be up, up because the lead coefficient is negative, then the end behavior will be down, down. Now, on the next one, we look at the lead term here. That is negative 5x to the 9th. Okay. And the lead coefficient is negative 5. And then the end behavior, while 9 would usually be, being an odd number, would usually be down than up. The negative flips it, so now it is up, down. One thing I forgot to do, I forgot to identify the degree. So degree is just the power of the exponent. So here it's 6, here it's 8, and here it is 9. Okay. Those are our 3 examples. All right, so we now know how to identify the lead term of a polynomial, which tells us how the polynomial behaves for, again, large values of x. Now, one thing that's important, one thing you may have noticed already, is that this tells us nothing about how the middle part behaves. Right? And here we don't know. But here we don't know. Here we don't know. All we know is how it behaves on the outside. So for this, we are going to need to know the zeros or the roots. I don't know why I have it typed up right there, but that's what goes in the blank. And so a polynomial of degree n, as you know, can be written like this, as we identified up here. But we can also write it like this, where we've got some number a factored out. And we got x minus cn, x minus c n minus 1, all the way down to c1. We call these c's the zeros or the roots because anytime you plug in a value of x for any one of these c's, it will result in 0. So for instance, if I plug c1 into the equation, well, at this term will be 0. Now, all these other terms will be some other number, but it doesn't matter how many of these terms are because they're all being multiplied by 0. So the end result is 0. Same with C2. That makes one of the terms being multiplied 0, so that means they are all 0. If I go all the way to the front, Cn, same thing. Everything will be 0. And so that's why we have, these are called the zeros. The term roots is because whenever you plug these in, if you were to graph this, it roots the graph into the x-axis. Okay, so moving forward here. We're going to go over something called the fundamental theorem of algebra. And so what the fundamental theorem of algebra says, it's all about polynomials, right? A polynomial a polynomial will have exactly the same number of roots as the degree of the polynomial. So we put degree in that blank. And remember, degree is just the highest exponent of the polynomial. So you'll have different types of zeros and roots. Some zeros and roots will be repeated. Like, for instance, if you have x minus 2 quantity squared, you would have a root of 2 twice, repeated. These roots can also be complex, that you can have an imaginary component. But what is important to know about this is that if the zero root is a real number, that is, it does not have an imaginary component, then the zero or root is called a x-intercept. So let's look at the case of a parabola, square, like which we now know as a square function, which is a polynomial of degree 2. So if you have 2 imaginary roots, well, that means you'll have a graph like this. There are no x-intercepts, right? Because all of the roots are imaginary. If you have one repeated root, well, then you'd have something that looks kind of like this, right? Only one x-intercept. It's repeated twice. Or if you have 2 real roots, well, then you might have something like this, with the roots being here and here. Okay, so these are the 3 scenarios you could have within a parabola facing up. You can have 2 imaginary roots, in which case you have no x-intercepts. You could have 1 repeated root, in which case you have 1 x-intercept. Or you could have 2 real roots, in which case you have 2 x-intercepts. All right, so now we're going to find the graph. Find and graph the zeros for the following functions. Take note of the behavior near the roots. All right, so I'm going to leave the graphing for you guys. I want you guys to go to desmos.com and pump these graphs into, go and write that there for you. Go to desmos.com. And graph these 3 and see what they look like, or just use a graphing utility. So here, we're just going to find the zeros. And so for this one, our zeros are -1, -1, and 2. So we can write this as -1, and write the multiplicity down there, and then 2, and write the multiplicity down here, because -1 happens twice, 2 only happens once. And so when you graph this, you'll find that near this square root, right, where you've got this root that is squared, I should say, you'll have a parabolic behavior. You'll find that near 2, it'll shoot straight through the x-intercept like a straight line. Verify this with a graph and zoom in really close to where the graph passes through the x-axis at -1 and +2. All right, so right here, we've got roots of 1, which happens 3 times, 0, which happens 2 times, and a root of 2, which only happens once. Okay. And for this last one here, we got the following roots of 1, which happens 5 times, 0, which happens 4 times, and then 2, which only happens once. Okay. So, like I was saying, near x equals 1 as it passes through, it'll act like a function of an odd power. When it goes through the x-axis through the origin, it's going to act like a square function. When it goes through a 2, it's going to act like a linear function. So I can get a fairly decent idea of the graph just from this information. So here, it's going to be of 6th order, which I've noted here, which means that it's going to be up, up. And we've got, let's see, 1, 0, and 2. And so this goes through, slides in, comes up. Oh, I'm sorry, it goes up. I was looking at this one. It pops up, and then it's going to come down. And then we're at 1, so that's going to slide through. And then we're going to come back up to 2, which goes through linearly. And it looks like that, right? So that's a quick sketch of this one. Let's go ahead and do this one right here. We've got -1 and 2 happening here and here. In behavior, like we got cubic, right, because square and then a linear. So this says we start in the down position, so come through, bounce off, and then we go through straight and then go up. So verify that with a graphing utility, please. Make sure this makes sense to you. All right, so note that the relationship between the behavior and the associated exponent in the function. So that's talking about near -1, note how it behaves like a square function. Right here, near +1, it behaves like a cubic function. So this exponent indicates the behavior of the graph near that 0. Lead term. So the lead term of the polynomial in factored form, that's the form we're looking at here in these 3 examples. In factored form, is found by multiplying the lead term of each individual term. So this means, note that the lead term for this guy right here is x squared, and the lead term for this guy is x. So 2 times x squared times x is x cubed, or 2x cubed, and giving us our end behavior. Okay, on this one, lead term for x minus 1 cubed is x cubed. Multiply x cubed by x squared and x, and then don't forget to divide everything by 100 as per this term here, and you will end up with x to the 6th divided by 100. All right, so let's do this example down here at the bottom. Find the lead term, end behavior, and zeros of the following equation. Sketch a graph of the result without utilizing any software. All right, so we immediately notice that we've got all the roots here. All the roots are real, so that means all the roots will also be x-intercepts. And so here we've got -3. Here this would be -2/3. I'm sorry, -3/2. And the last one will be simply 2. So that happens once. This one happens once. Oh, and whoops, forgot the 0. There we go. 0 goes with that one. It was kind of hiding. All right, so 2, that happens twice. The 0 happens 3 times. So those are our roots. -3, -3/2, so that's -1.5, 0, and +2. And we're going to go ahead and note the multiplicities down here. So -3 happens once. -3/2 also happens once. 0 happens 3 times. And then 2 happens twice. Okay, so we've got the roots noted here and their multiplicities noted down here. All right, so now we need to figure out the lead term so that we can figure out the end behavior of the graph. So lead term. So we just do the lead term of each individual term, x, and then we've got 2x here. Here that's just x cubed. And here we've got x squared. So we multiply these together to find that our lead term is 2 times, let's see, x to the 5th, x to the 6th, x to the 7th. Our lead term is 2x to the 7th power. 7 is an odd number, so that tells me we go down then up, being multiplied by positive, so no change happens. So this is our end behavior right there. So this tells us we start in the down position, this arrow right here. And this 1 says we go straight through. And then this 1 here. And again, note, I'm not really where it turns for right now isn't that important. It is important, but for right now, we're not going to focus on it. That's more of a calculus 1 that we're going to take a look at there. For right now, just as long as you get that it turns somewhere in here, that's fine. Basically, just kind of do a few test calculations to see how high your function goes. But other than that, we don't need a high fidelity here. We're just trying to get the idea. So we go through straight, come back up. Note the 3, that means we act like a cubic. Go up a ways, and then we come back down. Note that the 2 means that we're going to bounce off like a square. And that's it. That is a sketch of our function. All right, so now let's take a look in the other way. Now we've got a graph. Imagine you're looking at data, and you're trying to come up with a mathematical model to fit that data. So you might have, in a real world, you might have, dots kind of going, and you're just trying to, come up with a mathematical model that's going to help you predict and analyze what that data is doing. So to come up with this, first we identify the roots, which are right here and right here. And so this is -1 and 3. -1, since it bounces off, we're going to go with the lowest root possible. And 3, That is 1, right? That can only be 1. Technically, we might be able to work with 2, 4, 6, 8, or any others, but we're going to keep this as simple as possible. Go with the lowest exponent. So our function, right, we always want to include the a. Right, because it's the opposite sign of that. Plug -1, we get 0. And this will be squared as per the multiplicity. And then we got x minus 3 first to 1 exponent. Of course, the 1 is implied even if we don't write it there. So now we got this unknown a term. So in order to fit the curve, we're going to just find a convenient point to work. Note that we got one right here at the y-intercept at 0, 1. So we'll say at 0, 1. We plug that in. Right, y is 1, x is 0. So we've got a times 0 plus 1 squared times 0 minus 3. And so this turns into 1 equals a times -3. Divide both sides by -3 to find that a equals -1/3. And that is enough to get us our function, right? We plug that back into here. And so the mathematical model of this data would simply be -1/3 times x plus 1 quantity squared multiplied by x minus 3. And that would be our mathematical model, our answer for right there. All right, next example. Find the equation that models the polynomial graph below. So we identify our roots here and here. Note that goes kind of slides on through, so that indicates a degree 3. That one shoots straight through, so that indicates a degree of 1. And so our roots are simply -1 and +2. Multiplicity 3, multiplicity of 1 on each of those. So we plug this in to our model here, always an a, x plus 1 cubed times x minus 2, 1 exponent there. All right, so now we find a convenient point. We got the y-intercept again. And so we have 0, -1. So we're going to plug that in. At 0, -1, we get -1 equals a times 0 plus 1 cubed. And then multiply that by -2. And this will give us an a that equals a +1/2. Plug that back in to get our equation of y equals 1/2 times x plus 1 cubed times x minus 2. And there we go.